I was asked to give an introduction to multi-agent systems and where multi-agent systems came from, what multi-agent systems is all about, and where multi-agent systems might be going. Well, this is quite a big challenge now. It's a big challenge because multi-agent systems is now a very, very large research area. And there is no one idea that drives multi-agent systems. There are a collection of ideas, as I hope I will demonstrate in the talk this morning. But what I'm going to do is give you a feel for how the idea of multi-agent systems came about, how we originally began to think about multi-agent systems, and how that idea evolved, and what some of the main research challenges are in multi-agent systems, what we need to do to make the dream of multi-agent systems real, and how we might go forward on some of those, to give you a feel for just some of these ideas. Okay, so if we look at the history of computing, right since the very beginning, I'm going to argue that there are 5 trends that we've seen throughout since the early 1950s, when the first computers became practically available, through to the present day. We've seen 5 ongoing trends, and these trends have largely shaped the history of computing. So let's talk about these trends. The first trend is towards ubiquity, and this is just Moore's law. So Moore's law, we all know Moore's law. Moore's law says the number of transistors that you can fit on a square centimeter of silicon doubles every 18 months or so, some variation of that. But the upshot of Moore's law is that computers get smaller, faster, and cheaper. And that means that you can put computer processing power and hence intelligence of a kind, decision-making capability and information processing capability every year into devices that you could never think of doing previously. And so we're heading to a point where every artifact that we build is augmented with computer processing capability. It becomes economically feasible. It becomes feasible in terms of the size of the computing devices. It becomes feasible in terms of their power requirements and so on. So we could put computer processors everywhere. And that's the trend towards ubiquitous, towards an environment which is completely populated with computer processors. The second trend is more recent. It only became evident much more recently since around the sort of the late 1980s, mid 1990s, but is nevertheless one of the defining trends of computing over the last 50 years, and that's a trend towards interconnection. So when I was an undergraduate in the mid 1980s, I was taught programming on a standalone computer, and I was basically taught that was the expectation going forward, that computing would be all about standalone computers. Well, of course, that didn't turn out to be the reality, and it won't be the reality of computing for the foreseeable future. All of those ubiquitous processors that I talked about get connected to one another. They can all communicate. So we end up with a world populated with billions and billions, potentially hundreds of billions of computer processors, and all of those processors can communicate. That is, and when I talk about communicate, I mean there are pipes, the piping being the internet, being the wired internet, the wireless internet, down which those computer processors can communicate. And in contrast to the view that I was presented as an undergraduate in the 1980s, where computing was monolithic standalone devices, increasingly we're seeing a shift towards a view of computing where interaction is the fundamental component of computing. The third trend is towards intelligence. So obviously over the last 10 years or so, we've seen artificial intelligence take off in a very, very big way. But here I'm talking about something in a slightly more subtle way. All I mean by intelligence here is that the complexity of the tasks that we can get computers to do for us grows steadily year on year. They can do ever more complex things. So they become more intelligent. Now, this is not like a Moore's law. Moore's law is an exponential trend. A doubling every 18 months is like an exponential trend. The trend towards intelligence is very much not like that. It's a much, much, much slower rate of progress. But nevertheless, it's an ongoing trend. The next trend is towards delegation. And what this means is that we get computers to do things for us without our intervention. Every year, we're prepared to hand over more and more tasks to computers and get those computers to do those tasks completely autonomously. And by autonomous in this sense, I just mean without human intervention, right? So the human is not driving this. The machine is making a decision autonomously on our behalf without our intervention. So an extreme example would be fly-by-wire aircraft. So in the 1980s, again, if we go back to when fly-by-wire aircraft took off, no joke intended, there was a big debate at the time about whether this would be safe going forward, about whether we wanted to hand over control of something which was so important to a machine. Well, 35 years on, we recognize that flying is now a much, much safer activity because we have fly-by-wire aircraft, because humans are out of the loop, and because we delegated that task to computers. Well, of course, the next thing on the agenda is fly-by-wire cars, autonomous cars, driverless cars, intelligent braking systems, cruise control systems that maintain the distance from cars in front. All of these are now pretty much standard, and autonomous vehicles will, in the same way that that fly-by-wire aircraft made flying a much safer activity, driverless cars ultimately will make driving a much, much, much safer activity. So delegation, the trend towards handing over ever more decisions to computers. So far we've got ubiquity, computer processors everywhere, interconnection, those computer processors all seamlessly communicate with one another. Intelligence, the things that those processors do for us, getting more and smarter and smarter and smarter. And finally, delegation, we hand over control of more and more decisions in our lives to machines. And then the final trend is a bit more subtle. This is the trend towards human orientation. And what this means is that the way that we interact with computers gets more and more like the way that we interact with people. So if you go back to the very earliest days of computer programming, the very earliest computers in the 1950s, the way that you interacted with those machines was literally by flicking switches on the control desk of the machine. And flicking a switch this way would mean a 1, flicking it this way would mean a 0. And you literally filled up the computer memory by flicking switches in that way. And that was extremely time consuming. It was very error prone. You had to be an expert, not just in programming, but in the architecture of the machine that you were programming in order to be able to do it. So it was very unproductive. It was an extremely unproductive way of programming machines. And ever since then, we've moved away from machine-oriented views and ever towards human-oriented views. So what do we mean by that? We mean things like, firstly, introducing machine code, assembly language, so assembly language where you no longer have to remember the actual bytes that are used to represent computer instructions, but you can refer to them with mnemonics that humans can easily understand. Then the introduction of the first machine-independent programming languages, COBOL and Fortran in the 1950s. And the whole point about machine-independent programming languages, if you can program COBOL on this machine over here that's made by IBM, then you can probably also program in COBOL on this machine over here, which is not made by IBM. So you've got machine independence. And that meant that programmers had much more transferable skills and they could be much more effective. And then we started to think about ways of structuring computer programs, because one of the fundamental problems in computer programming is all about the structure of computing, a structure of large, complex computer programs. So first we saw subroutines, then procedural and function abstraction in the 1970s and 80s, through to abstract data types and objects in the 1990s. And then we moved on to the desktop folder file metaphor on user interfaces in the 1980s. And this remains the dominant paradigm for computer interface design today. And the point is here, we're moving away from machine-oriented views towards human-oriented views. And the point about the desktop metaphor, although we often forget it these days, is that it's called the desktop because it's supposed to resemble your desktop in your office, which has folders and files and a trash bin and so on. And these are metaphors that we all recognize and we all easily understand. So all of those trends have been evident since the earliest days of computing, and it is, I think, a very, very safe bet that that is what the future of computing, and in particular the future of artificial intelligence, will look like. The future of computing will be somewhere in that space of ubiquity, interconnection, delegation, human orientation, and intelligence. Now, I don't know exactly where in that space it will be, but it will be somewhere in that space with very, very high probability. I'm extremely confident that we will see all of these trends continue and that somehow they will manifest themselves in the future of computing. And because of that, we've seen many different realizations of that trend. So, for example, cloud computing emphasizes ubiquity and interconnection, right? The idea that there is just somewhere, you don't even know where it is, but there is some machine that you can interact with that will store your files, that will run your applications. There it's emphasizing ubiquity and interconnection. Peer-to-peer computing back in the early part of this century was a manifestation of ubiquity and interconnection. Ubiquitous computing and the Internet of Things. These are both big research areas. The Internet of Things, the idea of and ubiquitous computing, the idea of our environment being populated with computers that are equipped with sensors, providing information, and that the environment is adapting around us based on the information that those sensors are receiving. The semantic web, the idea that the World Wide Web is lifted from just being documents which have content to being documents which have meaning. So we augment documents with markup, which not tells us just how they are to be displayed, but actually with what they mean. And that markup allows machines to be able to do more intelligent things with them. And finally, the grid, another vision of computing from the early part of this century. But the version of the future that I'm interested in is particularly associated with artificial intelligence, and it's called multi-agent systems. So in AI, where that takes us to, when we think about ubiquitous, interconnected systems which act autonomously on our behalf, which are intelligent, and through which we interact with via human-like metaphors, that's what we call agents, sometimes call them software agents or intelligent agents or autonomous agents. But that's the vision of agents. So as a crude definition of what an agent is, it's an AI system which acts on behalf of its user or its owner. So it's an AI system which is acting on behalf, and crucially, it's acting independently. So the term that we use is autonomously. All that means in this sense is it's carrying on doing its thing without any humans telling it how to do it. And so it's given some task to achieve, some task to carry out, and it just gets on with that task and carries that task out completely independently or autonomously. So an AI system acting on behalf of its user or owner, and it's doing that independently. And it could be hardware, so it could be a robot or a car or a vacuum cleaner. So of course, the last example is by no means a frivolous one. So some of you will almost certainly have robot vacuum cleaners in your houses and apartments at the moment, and those vacuum cleaners will make their way around your apartment, hoovering up while you're not there. But in the future, where we expect to get to is to have these vacuum cleaners connected to one another so that they can cooperate and work together. So we can have teams of robot cleaners that work, for example, if one robot identifies an area of an office building which is particularly dirty, that it can call upon the help of other robots that are working in an area of a building which perhaps is not so dirty. So we've got an agent then, an AI system that acts on behalf of its user or owner, could be hardware or software, operating independently without human supervision or perhaps with limited human supervision, but crucially, operating in a social network of machines or software. So it's not just an isolated thing, it's something which is interacting with other agents, and those agents could be other software agents, they could be robots, or they could be human beings. Okay. So it's interesting at this point just to pause and reflect on how the idea of agents originally came about. Where the idea of agents originally came about goes back to the early 1980s. So in the early 1980s, Apple introduced the Macintosh computer in 1984, and the Macintosh computer was important because it was the first computer which was intended to be usable by non-experts. That is, you didn't have to have a degree in computer science or a PhD in computer science in order to be able to use it. And the key innovation was the desktop metaphor, the way that the graphical user interface through which you interacted with this machine made it much, much, much easier for people to interact with the computer. You didn't need to be a specialist. And it's because of that human orientation. The way that you're interacting with it is via things like files and the desktop and the bin and so on, things that we all recognize from our human world. And the Macintosh was, after a slightly faltering start, became a very big hit. And Apple very quickly started to think about what the next innovation in user interface design would be. What would come after the desktop? And they came up with the idea of the agent metaphor. So the agent metaphor was a vision to go beyond this. So 35 years on from the introduction of the Apple Macintosh, the desktop metaphor has been tweaked slightly, but it is still the dominant paradigm for interacting with computers. I'm doing it right now while I do this presentation with you. And the agent metaphor was the idea was to completely fundamentally change the way that we interact with computers. So the agent-based interface, the agent metaphor, is the idea is to shift from the idea of software as a passive servant to software as a proactive, cooperative assistant. So at the moment, when you interact with Microsoft Word or Excel or most other computer applications, everything happens because you make it happen. You click on an icon or you select something from a menu bar and so on. Everything happens because you make it happen. The idea of the agent-based interface was that instead of just waiting to be told what to do, you would have software which was actively working with you as an active assistant, taking the initiative, not just waiting to be told what to do, but taking the initiative in working with you. So that was the idea of the agent-based interface. And if this idea was successful, then the idea was that computer software would be like a human assistant. It would be working with you in exactly the same way that a human assistant would work with you on some task. And central to this vision was the idea of natural language interfaces, being able to talk to your agents. And this was important because in many applications, there really isn't any alternative. So in driverless cars, it seems that we're going to have to accept the agent-based interface because there doesn't seem any plausible alternative to it. You have to be able to talk to your car, your driverless car, to give it your instruction, because you can't start moving a mouse around to tell it what to do. Now, despite recent advances, and some of you will have played with GPT-3 over the last few weeks, which is a very, very impressive natural language tool, the idea of natural language interfaces, being able to interact with your agent through natural language, remains some way off. But nevertheless, we have versions of this reality on our desktop and in our pockets right now. And it took 20 years to make it feasible, but now we all have an agent in our pockets. So Siri, Alexa, Cortana, Bixby, these are all manifestations of that dream of having software which is no longer just a dumb recipient of our instructions, but something which is actively working with us, something which is working with us as a human assistant. And what made it possible is firstly Moore's law. computers got powerful enough to be able to carry around in our pocket. We all now have a supercomputer in our pocket. We have advances in AI that made voice understanding possible and natural language understanding possible, although we'll talk about the limitations of current natural language interfaces in a moment. And finally, the idea that the agent in your pocket doesn't have to do all the work. It's connected to a network, and it can use that network, it can utilize that network to call on other services that it doesn't have the capability to be able to process locally. So those three things coming together made, around about 10 years ago, made the primitive version of agents that we currently have, and it is still a primitive version of agents, Siri, Alexa, Cortana, and Bixby. That's what made that reality possible today. And what I want to emphasize is that these are just a manifestation of this dream, the idea of ubiquitous, interconnected systems that can work autonomously on our behalf, that are intelligent, and that are understood and programmed by human-like metaphors. And in this case, they're understood and programmed directly by natural language. They are direct realizations of that dream that we had of agents back in the 1980s, and fundamentally a shift from the view of software as a passive servant, software as a service, to software as a proactive, cooperative assistant. Okay, so what do we need to do to make this work? To make this dream of software agents a reality, which is still very much a work in progress, what do we need to do to make it a dream? Well, the first thing is that your agent needs to know your preferences. So what do I mean by that? So if your agent is going to go out and work for you, then it wants to do the best thing on your behalf. It wants to do the best thing for you. And to be able to do that, it has to know what your preferences are. So a simple example, if you imagine a software agent that you ask to book a flight for you, and a reliable flight booking software agent, something which could do this at the level of a human assistant, would be a tremendously useful thing to actually have. Well, in order to do that, it needs to know, for example, that you don't like flying via Paris airport because they always lose your baggage, that you prefer an aisle seat on an airplane, that you would prefer to spend a little bit more money to get a direct flight rather than have a stopover. All of those preferences which a human assistant would naturally take into account when they booked your flight, the software would also need to be able to have access to. So your agent needs to know your preferences. And giving your agent your preferences is very difficult. And one of the reasons that it's very difficult is that when you talk with a human assistant, like when you ask your secretary to book you a flight, she has in the background wide knowledge of the human world and of you, which she can take into account when she books that flight for you. So not just your preferences, but she can avoid doing things that a human being would think were really, really dumb, like, you know, avoiding 24-hour stopovers in some area, or very, very short turnover times at airports. She can, your human assistant would be able to make use of all of that knowledge. And computers don't have all that knowledge unless we give it to them. So all of that background knowledge also needs to be there. So firstly, your agent needs to know your preferences, and that is not trivial. One way that your agent can learn your preferences is by looking at past experience. So they can look at the flights that you have booked in the past, for example, and they can use those examples to learn about how to book flights for you going forward. But then there are some other skills that your agent is going to need to be able to have. It's going to be able to need to share knowledge, to communicate with you and with other agents at the knowledge level, in terms of the knowledge that the knowledge that you have about the world around you, to be able to communicate with you at the knowledge level. It's going to need to be able to share skills. You're going to potentially need to be able to train your agent to be able to do new tasks, and that agent potentially needs to be able to share skills with other software agents. It's going to need to be able to cooperatively solve problems. So your agent is going to go out and interact with other agents. That's going to imply the capability to cooperate, the ability to coordinate with other agents. Coordination we'll talk about in a lot more detail later on. The ability to negotiate with other agents as well. Okay, so later on in this talk, what I'm going to focus on is how we've gone about giving computer programs these capabilities, the ability to cooperate, coordinate, and negotiate with other agents. So I'll tell you about some of the techniques that have been developed in order to be able to make that feasible. Okay, what I want to focus on for a little bit now is one of the components of this vision of software agents, and that component is the natural language interface. So remember, our dream of the future of computing involves interacting with them via human-like metaphors. And the most important of those is natural language, languages like English or Korean or Mandarin or Russian. And this is essential because there are so many areas, application areas, where interaction via natural language is really the only possible alternative. And really it's about bandwidth. Just the way the volume of information that you can communicate with another person in natural language is just hugely higher than you can do through a keyboard in a computer programming language, for example. So natural language is incredibly important for the future of human-computer interaction and for the future of AI. But it's one of the earliest dreams of AI. So it was natural language processing was one of the first things that people tried to get to work with AI. And it turns out it's very, very difficult. It's a fearsomely tough nut to crack. And for 40 years, the dominant approach to natural language processing was to try to understand the syntax and the semantics of natural language. So when we have a computer programming language, we have two things. We firstly have a set of rules which govern how computer programs in that language are put together, and that's the syntax. And then we have a set of rules which define the meaning of those computer programs, what they actually do, how those instructions are translated into actions. And that's the semantics of the language. And the idea was that in the same way that we have these for computer programming language, we would also have them for natural languages. So the huge body of work that grew up around natural language processing was all directed towards trying to understand, for example, the syntax of English, the rules that govern the structure of English, and the semantics of English, the rules that tell you how a construction in English maps to the meaning of that sentence, what a particular statement in English looks like. Problem was it didn't really work. Natural languages are just too big, too cumbersome, too ill-defined, and too rapidly changing. Language is a moving target. It changes every year as people invent new constructions in language, invent new ways of using language. And that's just been an ongoing trend throughout recorded history and will be an ongoing trend throughout the future. So trying to formalize the rules of language in syntax and semantics didn't work. So, but we do have usable natural language interfaces. So how did those come about? Well, it was using machine learning and lots of data. Machine learning is what made this possible. And roughly speaking, the idea was that you would have what made machine learning possible, natural language understanding possible with machine learning, is that we could have large volumes of training data in the forms of large corpuses of written text. So for example, in translation, one of the basic natural language understanding texts, you would have a text in English and the corresponding text in French, and you would throw that at a machine learning algorithm, and it would learn associations between phrases or words in one text and phrases or words in another. And it turns out that if you have the right machine learning tools, you have enough of these translated texts, and you have enough computer processing time, then you can achieve usable automated translation. And usable automated translation is in the form of Google Translate or the many other tools that have become available subsequently, is one, I think, of the greatest triumphs of modern technology. That's an ancient dream. That's the dream of Babylon that's become a reality today. Okay, but you don't have to look very far to understand the limits of current natural language interfaces. You don't have to dig very far to find their limitations. They are mostly focused around very, very narrow tasks. If you look to Siri or Cortana or Alexa, there's a small number of tasks like playing a piece of music or controlling the temperature in your house or something else along those lines. A very, very narrow task. And if you step beyond that task, you quickly find that Alexa or Cortana or Siri are not very good at coping. So they are narrow and they are brittle. They often involve a heavy degree of scripting. And what that means is if you want to, for example, book a taxi, then there's a certain script that's associated with that. And the script is when do you want the taxi? Where do you want to pick you up? Where do you want it to take you? And if you want to go beyond that very, very narrow script, then you very, very quickly find that Siri and Alexa and Cortana can't cope with that. And also, an awful lot of natural language interfaces employ what I call chatbot gimmicks. That is, they're not really trying to understand what you're being communicated. They're just picking up on keywords and responding to the keywords. So a keyword being something like, you type in that you're unhappy today. It picks up on the keyword unhappy and simply responds, why are you unhappy today? It's not understanding the unhappiness that you have or making any attempt to understand the unhappiness that you have, but just simply picking up on that keyword and producing a predefined response to that. And people very quickly see those chatbot gimmicks, which are the fundamentally most of the techniques that are used in chatbots on the internet today, and they find them very, very irritating. So let's have a look at some of the challenges for natural language interfaces. And what I'm going to do is just pick up on a couple of very short examples that illustrate these. So here is a dialogue involving just 6 words. Bob says, I'm leaving you, and Anne says, who is she? Okay, so it's an extremely simple dialogue. I mean, human dialogue doesn't really get much simpler than that. But you all immediately understood this dialogue. And if I asked you questions about this dialogue, you would immediately be able to answer them. So for example, if I said to you, is Anne happy or sad after this dialogue has taken place? Well, it's pretty obvious, I think, that Anne is going to be rather unhappy after this, right? If I ask you to explain what's gone on in this dialogue, you would immediately be able to tell me that, well, Bob and Anne are in a relationship. Perhaps they're married. Bob has probably found another person. He's leaving Anne because he's now involved in another relationship. We might speculate that Anne was unhappy. We might speculate that Bob was perhaps not a very nice person. All of that. Now you immediately, just from those 6 words, have an incredibly rich understanding of this dialogue. Okay? You immediately have an incredibly rich understanding of this dialogue. And that understanding is grounded in your understanding of the human world. You understand human desires, human beliefs, human relationships. And we don't have that kind of understanding. We don't know how to give machines that kind of understanding. And if we are to have natural language interfaces which are truly rich, which are truly capable of interacting with us as cooperative assistants in the same way that a human would interact with us, then I would contend that I would contend that the computer would need to be able to understand that dialogue in the same way that you and I understand it. Okay, next example. So here we've got two sentences which are very similar, but they differ in just one word. So the first sentence, the committee denied the group a permit because they advocated violence. So my question is, who does they refer to here? Who is advocating violence? Is it the committee or is it the group? Now, I haven't told you anything else about this scenario. I haven't told you anything else about this scenario. I've just given you that one sentence, and I'm asking you who they refers to. Now, to be able to answer that question, you need to know something about committees, and you need to know something about groups. And so we might take into account the fact that committees tend to dislike violence. They don't like violence. Whereas groups that go on parades and so on can very often become violent. So advocating violence, the group that the people that are advocating violence are the group in this case. Okay, so the second sentence is the committee denied the group a permit because they feared violence. So who fears violence? Is it the committee or the group? So again, we immediately pick up on that it is the committee that is, in this case, that is fearing violence. They, in this case, refers to the committee. Now, the difficulty here is, in order to be able to understand these very subtle differences in sentences, which would again be crucially important in any kind of natural language, okay, in order to be able to understand these two sentences and the differences between them, you have to have some knowledge of the human world. You have to know about committees, you have to know about groups, you have to know about violence, you have to know about permits. And we don't know how to give that knowledge to computers. Okay, so we don't know how to give that knowledge to computers. So resolving references in this way is a huge challenge for natural language processing. And by the way, if you want to look up some examples, these are what are called Winograd sentences. These sentences, these very subtle sentences, excuse me, which change in just one word. These are called Winograd sentences. Okay, here's another example. So here is a kind of thing that you might naturally, if you were talking to your wife or your daughter or your husband, and you were in a car driving somewhere, this is the kind of thing you might sort of very often say. So, hey Siri, play that song we listened to a lot on the way to Cornwall that time, the one that Lily and Tom argued about. So in order to be able to understand the context of that sentence, you need to be able to understand a journey to Cornwall, a song that you listen to a lot, and an argument between Lily and Tom. Right? And that's the kind of thing that your family would immediately understand the context of. But for a computer, even if Siri has been listening to you permanently, understanding and maintaining context like that is really, really hard. For it to be able to make sense of those experiences and to understand the song that you are referring to there, the song that your family would immediately understand and remember, is tremendously hard. So all of these examples are to point out that rich natural language interfaces and interacting with agents via these human-like metaphors remains some way in the future because of scenarios like this. In order to understand this incredibly simple dialogue, you have to be able to understand something about human relationships, human beliefs, and human desires. In this scenario, you have to know how to be able to understand, you have to have some knowledge about groups, about permits, about committees, and about violence, about what groups do, about what committees do, and about what committees like and dislike, they dislike violence, and so on. And for this example, you need to be able to understand and refer to long-term context, understanding the context of some particular scenario, and relate the natural language that's being used now to events that have taken place distantly in the past, for example. So rich natural language interfaces remain some way in the future. So that's one of the driving challenges. And I don't know if anybody of you have played with GPT, but if not, I urge you to do so. GPT, an incredibly powerful system going forward. Okay. So what I now want to do is to shift away from human to agent interaction of the form that we have in Google Duplex and Siri and Alexa and Cortana, where a human is communicating with a software agent or a robot, right? In the examples that we've seen so far, that's what's been going on. We've had a human that's talking to a computer, and shift towards agent to agent interaction. So this is, I said to you that we had back in the 1980s, we had the dream of software agents. And one of the components of that dream was that it wouldn't just be us talking to agents, but that agents would talk to other agents. Agents would interact with other software agents. So to use a dumb example, if I want to book a meeting with you, why would I phone you, or why would my Siri phone you, right? So Google Duplex, for those that haven't seen it, this is a piece of software that can be used to, for example, book a meal by phoning up a restaurant, and it will phone up and book a table for you for 4 people at 8 o'clock and so on in your favorite restaurant. And it's an agent, a software agent, which is talking to other human beings. But actually, if you pause and think about it, that makes no sense. Why would this agent waste the time of another human being? Why doesn't the agent talk directly to, why doesn't it talk directly to another agent, to a software agent? Why doesn't my Siri talk to the restaurant Siri? If I were to book a meeting with you, why doesn't my Siri talk to your Siri, and your Siri look at your calendar and my Siri look at my calendar? So this is agent-agent interaction. Now this is a component of the dream of software agents, which we all thought would happen as a natural part of the realization of the vision of software agents, because it just seems so natural. If we're going to have software agents that work on our behalf, then why wouldn't they interact with other software agents? But while we've seen the vision of agents being realized in the form of Siri and Alexa and Cortana, what we haven't seen is those agents interacting with each other, which I say is what we thought was a very natural part of the vision. So what I'm now going to do is to move on to the second part of the talk, is to focus specifically on that aspect. And there are really 2 questions that you need to address. There's kind of agent design and agent social network design. How can we build agents that can work on our behalf and carry out the tasks that we delegate to them, right? So how do we do that? And machine learning and reinforcement learning has been tremendously important in making that happen. And the second part of the question is, how do we deal with these questions of agent-to-agent interaction? How do we build agents that can cooperate, coordinate, and negotiate with other agents in order to be able to successfully carry out these delegated tasks, especially when the other agents cannot be assumed to share the same interests or goals? So this last point is important, and it's worth picking up on. Suppose I'm going to delegate to my software agent the task of buying something or selling something, and it's going to interact with your software agent. So let's say I'm selling and your software agent is buying. Well, your software agent wants a low price, my software agent wants a high price, right? Here, the goals of those 2 agents are different. So how do they interact with one another in that particular setting where the goals are so fundamentally misaligned? Okay, that's the agent network design problem. How can we build common languages so that these agents can communicate, or more likely, common service interaction platforms so that they can interact with one another in scenarios like buying and selling. So these two fundamentally different questions. We've made an awful lot of progress with respect to the first question. We've made much less progress with respect to the second question. And so it's the second question that I'm going to focus on primarily in this talk. It's worth pausing for a moment to talk about when a multi-agent solution is appropriate. So when should you be thinking about a system as being a multi-agent system? And there are a number of points here. So one is where data and or control are inherently decentralized and they cannot be centralized for whatever reason. So here where you're talking about multiple centers of control where decisions are inherently localized, it starts to make each of those to think of each of those decision-making centers as if they were an agent, as if they were a software agent. Where a central viewpoint is impossible or undesirable, that is, where central control is inherently impossible. Where the stakeholders have competing goals, where there are components of the systems where the preferences of the agents are not aligned with one another. So where there are competing goals. And finally, where cooperation or agreement is a key component of the problem. That is, what your system is all about is reaching an agreement or reaching cooperation. So whenever you've got a system with these characteristics, data and control are decentralized inherently, it cannot be centralized. There is no possibility of centralized control. A central view of the system is impossible or undesirable for whatever reason. Where the components of the system have competing goals, their preferences are not aligned with one another, or where cooperation and agreement is a key component of the problem, these are all situations in which a multi-agent solution might be considered. So what I'm now going to do is I'm going to talk about three skills. Excuse me.